answer 3 questions: why, how, and what now. So why flood forecasting? Why are we interested in doing flood forecasting? How can data assimilation help? And what now? How can we improve the current operational situation? So why flood forecasting? Well, floods cause a lot of damage. This plot is of the US dollar damage as a result of floods in any given year, so with the years along the bottom from 1980 to 2025. And you can see it costs a lot of money, so it has a huge financial impact. And obviously with climate change, we expect more frequent, more intense events as we go forwards in time. But as well as the financial costs of flooding, there's a big human cost. So you can see from these newspaper headlines, people die, people get ill. So there's often a problem with contaminated water during floods. And also people suffer from big mental health impacts from being flooded. So it's not just about the financial cost, it's about the human cost as well. So river flood forecasting. So I'm going to focus on river floods as opposed to coastal floods or surface water floods or groundwater floods. For river flood forecasting, typically what happens is we chain together a bunch of models. That includes numerical weather prediction models. So we predict rainfall, for instance, with numerical weather prediction. And that information goes into a hydrological model that routes the river water, does some runoff and river routing into a river discharge. But that doesn't tell you, that tells you if a river's likely to overtop its banks, but doesn't tell you where the floodwater is going to go. So that gets chained to something called a hydrodynamic model, which typically solves the shallow water equations or an approximation of the shallow water equations to map the flow of water over the land to work out the flooded locations. And that gives you a flood map. And sometimes that's intersected with vulnerability indices, things like population density or where particular infrastructure is, to give you a flood impact map. So you can imagine that this is quite a time-consuming chain of models. We all know that numerical weather prediction takes a long time, it's very expensive, but then if you also have to do hydrological modelling and hydrodynamic modelling and do this intersection with the vulnerability data, then actually your forecasting chain becomes quite difficult computationally to actually produce the forecast quickly. So what people often do, particularly these days, is you might replace these last two stages by a simulation library. So you have a set of computed flood maps, pre-computed flood maps, and then you use your river discharge value to help you select which flood map you think is most appropriate for the current situation. And with a big chain of models, there's obviously lots of uncertainties, and they can come from the meteorological forcing, from the numerical weather prediction, or from observations that go into the hydrological model, initial conditions for each of these models, and model structure and model parameters. So where can we put data assimilation into this problem? Well, I think many of us will be quite familiar with the idea that we do data assimilation for numerical weather prediction, but can we slot it into the process for each of these other models, for the hydrological model, the hydrodynamic model, or the flood impact mapping? Well, I'm going to talk today about two applications, one which is for the global north. So it's a European flood hydrological model. And I'm also going to talk about flood mapping applications in the global south. So let's go to the global north application first of all. So this figure over on the left it's from a paper by my PhD student, Gwyneth Matthews, and it shows river gauge stations over Europe. So each little dot is a river gauge station, which provides data to the European Flood Awareness System, which is part of the Copernicus Emergency Management Service. And the colours of the dots, the blue dots are stations that only provide historic data. So that data is not available in near real time. And the green dots are the stations that do provide near real-time data. So you can see there's a lot of stations, but not all of them are providing it in enough time that you could actually use it for a data assimilation situation. So sometimes the data comes in weekly, sometimes it comes in monthly. And sometimes it comes in near real time. So if you want to do data assimilation, if the observations are not arriving in time, it doesn't make it feasible for forecasting. So what often happens with hydrological modelling, and particularly in this system, the European Flood Awareness System, is observations are used for post-processing to reduce uncertainty and improve forecasts. So this is kind of a zoom in of the previous map, slightly different colours, but this is the Rhine catchment, and each red dot is a river discharge station. And the problem with post-processing for hydrology is that you only correct forecasts at gauge locations where we have observations. So we can only do the post-processing at each of these little red dots. So because we have a spatially inhomogeneous river network, we can't just spread the information from the post-processing. Some of these rivers are quite large and you can see some quite small tributaries. So a correction that might be right for a large river might not be right for a small tributary or distributary. And only 1% or so, 1.15 of this catchment, the Rhine-Meuse catchment, is observed. So what do we do about all those ungauged locations? Can we use data assimilation to help? So what we've done with Gwyneth's PhD was try to use data assimilation not at the usual point in the forecasting chain, i.e. not before you run the hydrological model, but actually after you've run it to do some post-processing. So we use an ensemble Kalman filter idea, and because we already have a pre-computed ensemble forecast, but I'm going to call it a hindcast because we've already produced it, what we need to do is generate something that we can ensemble. So what we do is we have an error ensemble, something maybe you could imagine it's like a model bias, a state-dependent model bias. So we generate an initial error ensemble, and one of the things we found is that's quite important to make that physically consistent with the river network. And then we do state augmentation, which is a technique that's commonly used with data assimilation for things like parameter estimation and model error estimation. So we take our ensemble that we had, each ensemble member this is in grid point space, we turn that into a vector, and we have our ensemble of model error terms, and we put them on the bottom of that vector, so we kind of drag them on the end. So that's state augmentation. And then we do the usual kind of ensemble Kalman filter step. We have to use localization, we have to use inflation, but then once we've done that, we also enforce another physical constraint to make sure that we have non-negative discharge. Because we're correcting only this bias term, our correction might end up being a bit too large, particularly for small rivers, and we find that we sometimes get negative river discharge, which is obviously unphysical. So we have to do something to make a correction, which is to make it, we just set it to a very small value. So once we've done our ensemble Kalman filter step, we're able to add our error ensemble onto the initial hindcast ensemble to adjust to provide ourselves with a post-process forecast. And the hope is that that fits the observations better. And then instead of having the usual forward state propagation step that you would have, you would normally have a forecasting step in an ensemble Kalman filter. Again, we're using the existing already computed forecast or hindcast to do that forward propagation. All right, so does this method work? So we've done some experiments again with this Rhine-Meuse catchment, which is one of the biggest and best instrumented catchments in the EFAS, the European Flood Awareness System domain. And this is just an example for high flow. So we've done some single observation experiments with two different locations. So one is Bonn, which is this blue dot here, and the other one is Akanga on the Moselle, which is this other blue dot here. So the first panel is the single observation experiment for Bonn, and you can see the different colors give the analysis increments, and you can see the effect of localization here because the gray areas are where there's no increment, okay? And similarly, we have a single observation experiment for Akanga, and it seems to be behaving reasonably well. If we assimilate all stations again, we have the correct kind of behavior. Okay. In order to make sure we get physically consistent results, we do need to be very careful about how we put in this river network, because you don't want increments on a mountain where there shouldn't be any water. Okay. So most of the time, if we look at what happens as a function of time, we're mostly better at capturing that river discharge experiment. So because we had quite a nice instrumented catchment, we did leave one out experiments where we assimilated all the observations except for one in order to test the behavior and use that location as an independent location to work out if we were doing better or not. So this is just one example, and here's a blue dot at the top at the location Ries, which is on the main Rhine River. So in the colors, so this is a function of time, and this is discharge on the y-axis, and the colors are the raw hindcast, so the lighter colors are the individual ensemble members, and the darker color is the ensemble mean, and then the purple is the corrected hindcast member, the post-processed members, again with the darker color being the mean and the paler colors being the individual ensemble members, and the black dots are the observations. So you can see that in this nicely selected example, we do actually have better behavior. We're better fitting the observations. We've got a little bit more ensemble spread, which again might actually be helpful for users who know that there's a risk of something bigger coming. So we get a temporary consistent improvement. We don't find that we're getting big jumps every time we correct the ensemble. So that's great. The bottom plot here is for the same location, but it's for a time when the filter doesn't work so well. So this is for the falling limb of a flood, so when the flood is going down. And you can see that initially the raw hindcast ensemble, so the yellowish orangish lines, have a very small spread at short lead times, which does extend at longer lead times. And so we find that the data assimilation inherits that spread from the hindcast ensemble, and it's actually not able to correct using the observation information because the ensemble's overconfident, and that's can be a typical problem in the falling limb of a flood that we found. But on average, it does better. So Thinking about how this does in general, before we move on to the second topic. So we found that this approach is useful. We can improve the hindcast's ungauged locations using our new ensemble Kalman filter with a pre-computed ensemble. It on average does better. It typically doesn't make things worse, or at least in a neutral way. So it's a useful technique. It's not perfect, as things never are. But it was really, we found that in designing the method that we had to be really careful and think quite carefully about our specific application in terms of physical consistency. So it was really important that the filter knows about the river network and knows about the fact that discharge is physically always 0 or positive. The other advantages of the approach, which is perhaps a broader advantage for post-processing in general for flood forecasting. So we use those in situ river gauges, but there's nothing about our approach that couldn't be used with satellite data. So for many locations in the world outside of Europe, there isn't necessarily a great river gauge network. So if we're able to use satellite data or even camera-based sensors, we could use them as long as we have a suitable observation operator. And the only thing that is a blocker to using this in operations at the moment is that, of course, as I mentioned at the beginning, there's this data latency problem. So the gauge data actually is not available even in time for the operational post-processing in many cases. So what we've considered doing, and what Gwyneth put into her PhD thesis even, was actually using these existing post-processing techniques that use kind of historical time series of data at gauge locations to work out a post-processing correction, could then be used as proxy observations. So instead of assimilating real observations, we assimilate post-processed fields at specific gauge locations and then spread that information around. So, and we found that that did also improve the post-processing at the ungauged locations, but it wasn't as big an improvement as using the actual observations. I guess that's not so surprising if the post-processing itself is imperfect as well. So it did well where the post-processing worked well and not so well where the post-processing wasn't working so brilliantly. So that's an exciting development, and we'll look forward to seeing where that goes in the future. So now we'll move on to the second application that I wanted to talk to you about, which is for the global south. So countries where perhaps they don't have their own operational flood forecasting service, or where that is not well communicated to local populations. So for those kinds of situations, JBA Consulting have set up this new system called Flood Foresight. And what they've done is produce a lot of pre-computed flood maps using some of their software, RFlow and JFlow, which are quite well-known flood mapping hydrodynamic hydraulic models. And they've produced these flood maps based on designed flood events, so that gives them a database of flood rarity to look up different flood events. So if it's has an annual exceedance probability of 10%, or another way to say that kind of thing would be, a 1 in 100-year event or a 1 in 10-year event. You can look up a designed flood that would look similar to that. So that gives you a library of flood maps for different thresholds or different probabilities. And And you do that over lots of small regions, so hydrological subunits or impact zones. So you have this static pre-computed flood map library. And then when you want to use it for dynamic operational and impacts mapping, you take output from an operational hydrological model. So in this instance, they use the GLOFASS model, which is the Global Flood Awareness System, which is another service of the Copernicus Emergency Management Service, which is similar to the EFAS model I just showed you, but global. And you have specific locations you may be looking. You have a threshold value that gives you a warning that a flood may be on the way. You use that value in a lookup table to decide which flood map to select. And then you select the flood outline with the closest match to in-river conditions from your flood map library for each of these small areas, impact zones, and then you stitch a map together with all of these impact zones. And each of these little maps is a 30-meter resolution map, so it gives you some quite high resolution information driven by something that's really quite low resolution, the hydrological model. So that's the flood foresight system. And how does that connect with actually helping people? So this actionable information, what actions can people take? So in the Global South, there's been a lot of activity on disaster risk financing models. So you may have some kind of agency, that could be a government agency, it could be a non-governmental organization, but you'll have some kind, it could be the Red Cross, for instance, a humanitarian organization, and so on. That agency will do some work to assess the flood risk in advance. So that might take into account vulnerability to flooding, what the hazards look like off these designed flood maps, and the exposure. So who lives there, what's the infrastructure, what are the potential issues, and that gives you a flood risk profile, and that enables you to develop a plan and set aside a resource for different scenarios. So that plan might be, you may have different plans depending on what the impact is expected to be, and also what the likelihood is. So you may have a high impact but low likelihood event, or a low likelihood event or a high likelihood event that's low impact. So you design your actions and what you're going to do in advance. You have a trigger to tell you what's going to happen. Okay, so you can use these triggers in advance of the flood, so that's called early action, or sometimes forecast-based financing. So we use the forecast as a trigger to release funds, activate the plan, and that enables you to take early action to reduce impact. So if it's a low likelihood event, you might decide to do a low regret action. So that's something that isn't necessarily very expensive and that you won't be sorry about doing. If it's a high likelihood event, you might take more radical action. So a low regret action, for example, can be as simple as handing out plastic bags so that people can put their important documents in them. The other approach is early response. So, and that's sometimes called parametric insurance. So instead of using your forecast as your trigger, you use the event actually happening as a trigger, but you have a method of checking and monitoring the events, which you might not do otherwise. And then that trigger enables you to mobilize resource and your plan very quickly after the event has happened. So that means the affected area receives help more quickly. And again, that reduces the impact of the event. So how is it possible to evaluate and improve a system like that? Well, You can join together this flood foresight type forecasting model that forecasts the flood impacts with for instance, by intersecting the flood hazard map with population data. And you can use that system in your forecast-based financing system as your trigger to release funds. So JBA have been working with a group called the START Network, which is around 80 to 100 humanitarian organizations, both international ones and local ones, that take the trigger information and move into action as soon as they get that forecast-based trigger. So we've been looking at how you can evaluate and improve a system like that. There may not be very many reliable local observations of what's actually happening. So we've been looking at using satellite data in order to do that. So one example here of a high quality product that we can do that with is something called GFM, the Global Flood Monitoring Product, which comes from the Copernicus Sentinel-1 satellite, which is has a synthetic aperture radar instrument on it. Synthetic aperture radar is active day and night. It's an active instrument, so you can see through clouds, it can see day and night, but it does have problems in urban areas. So over here on the left is an image of the flood likelihood for the Indus Basin in Pakistan. So the orangey colours are a percentage of flood likelihood. So the deep orange is it's definitely flooded here, 100% flood likelihood, and the paler colours are lower likelihood of flooding. You can also see there's quite a lot of grey areas here, which are the areas that have been masked out. The other parts on here is the river, so that's the permanent water body, PWB, in blue, which goes around here, and these areas that are outlined in cyan are the areas that we're going to do some data assimilation for, which I shall show you in the next slides. So one of the key issues is that urban areas are part of these masked out grey, and that's partly because this SAR is an active instrument. So in an urban area, the buildings get in the way. As this little picture shows, you have you're measuring the backscatter from your active pulses, and you find the buildings can cause shadows. They can cause something called layover and double scattering, where you have that double bounce problem. And so what you get back is not the bounce off the water surface, but actually the bounce from the water surface to the building and back up to the satellite. And that makes it really hard to know what's happening in urban areas, which is, of course, where the floods have biggest impact. That's where the people are. Okay, so what was our plan? So we decided we were going to try and use this SAR data and assimilate it using this simulation library to provide a secondary improved flood map that might act as a secondary trigger in your forecast-based financing. So you've got your forecast, but then maybe you have your event-based trigger as well. So it's a combination of forecast-based financing and parametric insurance. So we have a forecast state, and there may be one of the catchments that's modelled that doesn't have a trigger for a flood map. Okay, and so we're only really interested in the places that haven't triggered in the forecast-based financing, to make sure that if they are flooded, they also get support, because once they've been triggered, the support is already mobilised. Okay, we use the observation data from the SAR, from the GFM product, the flood likelihood layer. So we have a probabilistic flood observations, and we combine them with the simulation library, which is our subcatchment flood extent and depth maps. We minimize a cost function, and we produce an updated state, which gives us a new flood map. So how does it work? We have our GFM likelihood. So the likelihood in GFM has binary observations. So the observations say it's a 1 for flooded, 0 if it's unflooded. But we also have this likelihood layer, which is the likelihood value from the product. So this is this percentage or probability of flooding at each location. So that gives us a probability distribution, a binomial distribution that looks like this, with our observation operator saying the state is 1 if it's flooded, it's 0 if it's unflooded. Okay. So we take the log of that likelihood to give us a cost function. So that ends up with two terms. One is the likelihood of flooding, and the other one is essentially coming from the log likelihood of being not flooded. We have not put a background term in here, although in principle you could. And when we minimize this cost function, we're going to minimize that over the flood map library. So that's 36 possible states divided into impact zones. So we're not trying to minimize over all possible states. We're trying to minimize over a kind of a physically constrained set. The advantage of that is that those flood maps are already linked to specific actions in the sort of parametric insurance system. So what we did was we analysed these pale blue outlines impact zones that were not already forecast for flooding, so they weren't already triggered for forecast-based financing payments, and we included different types of locations, and then we evaluated our findings with an independent source of flood data, which was this data from Sentinel-2, which is visible in near-infrared bands. And you can produce a normalized water index to provide you with information about when things are flooded or not. So,
Sarah, just a quick warning. You have about 4.5 minutes left.
Brilliant, thank you.
Including questions.
Yeah. So I shall keep moving rapidly through. So I haven't got enough time to go into detail here, but we found that when we're near the flood edge, that works best. We can find an analysis flood map that gives us a trigger, and even though that might still be an underestimate, which is given in the red in this bottom plot here, it doesn't matter that it's an underestimate because at least it's triggered. Okay, in the urban areas, so this is an example of an urban area. You can see there's a lot of grey masked out in the SAR. There wasn't enough information to actually trigger a flood map in the central urban area. However, when you have a mixed area that's part urban and part rural, you do have enough information to actually trigger the flood map again, because the information from the rural area is effectively physically interpolated using the flood map into the urban area. So that was great news, because as I say, these observation data can't normally be used in urban areas, so we can use the model to help us physically interpolate the information from the observations into those urban areas. All right, so this flood forecast-based financing work, so we have this new data assimilation framework that works with a simulation library to improve flood map selection for these forecast-based financing and parametric insurance applications. While the GFM observation product is masked out in urban areas, the information from the rural areas can inform flood map selection as long as we have a mixed impact zone, so we're not just exclusively urban, so we have enough observation information that will give us some value. So what's the outlook for operations? Well, that GFM product is available 8 hours after the SAR acquisition. So that's still useful as a potential secondary trigger, because the calculations we were doing were not particularly expensive, and particularly if you only apply them to areas where maybe there are neighbouring neighbouring zones that have been triggered for forecast-based financing, and you've only got 36 flood maps to optimise over. So that's something that may be explored with JBA in the future, to think about operationalising this with their clients, people like the START network. All right, so overall, what's our outlook? I've shown you those two different applications of data assimilation in that flood forecasting chain. It is possible to work on the other parts of the flood forecasting chain as well, and we have done some of that before. But the main message is that we can use data assimilation ideas to inform flood forecasting and provide that critical, actionable information to help mitigate those floods. But when you're developing these kinds of approaches, you really have to go in and understand the constraints. So one issue is observation data latency, or even complete lack of observation data in some areas. And the computational time for modelling available is a lot less, partly because you've got to wait for the weather forecast to be created first, but also often you're in applications where there's not a huge amount of computer power. If you're working for a local humanitarian agency, you're not going to have a lot of computer power, or you're not going to be able to invest in a lot of computer power for other people to do the computations for you. So whatever you do has to be quick. And the other thing is that bringing in physical knowledge is really important. So in hydrology, that was the river network. In the flood mapping, we use those pre-computed flood maps to help spread information from the rural areas to the urban areas. So that's it. I'm excited about applying DA to new applications, but as I say, you really need to think quite hard about how that application works, and not just apply what you know from numerical weather or ocean prediction. All right, so that is it from me. Thank you very much. Let's see if I can stop sharing.
Thanks for the nice talk. We are slightly over time, and there are quite a few good questions, but I think none that can maybe be answered in a very quick way. Maybe one from Tom White, who asked, roughly on like slide 17, you were showing these cyan areas, which were impact zones. How did you decide what these impact zones were? Or how were these determined?
So they come from the hydrology, so they're kind of subcatchments, and so they're linked to particular grid cells in the global hydrological model. But they're also linked to different vulnerabilities in the local area. So they're not necessarily decided by you as the data assimilator, they're decided by the authority that wants to produce the parametric insurance or forecast-based financing actions, but they are physically consistent usually.
Okay, thanks. Then before